Good afternoon, everyone, and welcome back from spring break. We're ready to get started in with our next unit, which is going to be the mole. Now, in terms of this mole, it's not the same one that we normally think about, although we will have a little bit of a project. Check your packet, and you'll see all the outline of your mole packet, your mole project, that we're going to have as a part of this. But this mole is going to be the one that scientists and chemists use to actually be able to understand how molecules can somehow make it into these reactions that we talk about and how we can actually calculate and use this information. Now, before we get started, you need to go ahead and rate yourself. Where are you at on this scale? Maybe you learned a little bit about the mole before this point, so you know you have a little leg up on it. But the goal is by the end that we want to be able to get you to this level 3. We want you to be able to explain the purpose of the mole, why we have it, and actually be able to use it in being able to calculate or convert, between moles and representative particles. And we'll talk about that in just a second. Now, let's get started. What is a mole? Well, a mole is a counting unit. Similar to like we use a dozen or a pair, different things like this. But it's a much, much larger number, 602 billion trillion. We talked about this earlier in the year. We sort of mentioned it a little bit. But now we're actually going to get into how we utilize it in chemistry or in this class. Now, the way that we write it to make it a lot easier without having to guess and write how many zeros is writing it as 6.02 times 10 to the 23rd. This is, of course, written in scientific notation, but we named it Avogadro's number in honor of the gentleman who actually came up with this. Now, this is an actual calculated number and value, so it's not just something we made up off the top of our head. But it's made this way so that we don't have to count up some of these other situations that are going to come up. Now, to give you a little bit of perspective on how big a mole actually is, think about it this way. If I had 1 mole of soft drink cans, or pop cans, or soda cans, whatever you say from wherever you might be in the country, it's enough to cover the surface of the earth to a depth of 200 miles. So imagine all those Coke cans stacked up, spread out all across the surface of the earth. This is what we're dealing with in terms of number. A couple other ones that we have here. You had Avogadro's number of unpopped popcorn kernels. You could spread them across the United States, and the whole country will be covered to a depth of 9 miles. We know how small a popcorn kernel is, so to think that the entire country would be covered to that depth is an astounding number. And the last one, which is the one that really puts everything in perspective and helps me to see how large of a number we're dealing with here. If we were able to count atoms at a rate of 10 million per second, so we have the ability to count 10 million atoms per second. It would take about 2 billion years to count the number of atoms in 1 mole. So we're dealing with this huge, huge number. But the question is, why is it so large and why is it so important that we actually know this? Well,
avocados are tasty.
Well, as my wife added in, avocados are tasty, but that has nothing to do with what we're doing here. Now, just to give you an idea, again, going back with using it as a counting unit, like if I have a dozen cookies, if I have 1 mole of cookies, I have 6.02 times 10 to the 23rd cookies. That's a lot of cookies, and that would be a wonderful, wonderful birthday present, but I don't think anybody could actually make that. A dozen cars, 12 cars, 1 mole of cars, 6.02 times 10 to the 23rd. Aluminum atoms, the same type of idea. No matter what it is, it's just a counting unit. So however many moles, multiply that by that 6.02 times 10 to the 23rd, and that's going to give us an idea of how many atoms, molecules, particles, whatever, are involved. Now, note that the number is always the same, but the masses can be very different. There's a big difference between the mass of a car and the mass of a cookie. And of course, last on this slide, how do we abbreviate mole? Well, we just write it as MOL. As you see, yeah, we dropped the E, but hey, you're going to use it a lot throughout this class. Now, you always have to make sure that you include your units so we know which direction we're going, what we were converting from, what we converted to, and finally actually got to. So, as one teacher says, no naked numbers. None. Okay? We cannot have it. Now, these representative particles that can be represented usually in a mole that we deal with is atoms, molecules, ions, and formula units. Each of these we've dealt with before. Representative particle for an ionic compound, you guys should actually be able to tell me this one, but would be an ionic formula. Representative particle for covalent compound is going to be a molecule, and then representative particle for an element, of course, an atom. These are, whenever we see how many particles, formula units, any of those things, we know that we're going to be dealing with that 6.02 times 10 to the 23rd number. Anytime you see this, how many blank in however many moles, this is giving us the idea of what we're going to be dealing with. Now, when we deal with atoms, molecules, or so forth, it's going to be the same idea. I feel like I'm repeating myself a lot, but I'm going to repeat it a number of times to make sure that it is very clear. So if I have 1 mole of carbon atoms, that means I have 6.02 times 10 to the 23rd carbon atoms in that 1 mole. If I have 1 mole of water molecules, and notice I'm changing the representative unit that I'm dealing with here. First when I was dealing with atoms, now I'm dealing with molecules. I have 6.02 times 10 to the 23rd. And last but not least, if I have 1 mole of sodium chloride, that means I'm really dealing with 6.02 times 10 to the 23rd formula units, not molecules. I need to change that. We do not deal with molecules for ionic compounds. It is formula units. Now, understanding that piece, that means that I also have to have 1 mole of sodium atoms and 1 mole of chlorine atoms, because remember, they're not actually bonded together, they're just attracted to each other. So we're going to use this information now to move in the direction of, okay, what do I do with it? Now, if you remember earlier in the year when we dealt with our dimensional analysis, which I know a lot of you are saying, oh yay, I love it so much. Well, when we dealt with our dimensional analysis, we had these conversion factors that we had to deal with. The wonderful thing about dealing with Avogadro's number, or how many particles, atoms, molecules, we only have one conversion factor. It can just be written 2 ways, one of 2 ways. It can be written with the number of particles, 6.02 times 10 to the 23rd particles over 1 mole, or 1 mole over 6.02 times 10 to the 23rd particles. That's a wonderful thing for us actually, because when it comes to how many, we don't have to think too much, but we need to memorize this number. This is going to be like our best friend over this next unit, okay? Now, we want to do a little bit of a learning check and sort of get an idea of what's going on here. Now, I wish I could pull up my calculator on screen, but I don't have that ability at this moment. But let's take a look at what we have here. If I was to ask how many or what number of atoms do I have in 0.5 moles of aluminum? Well, we can do this one of 2 ways. We know how many atoms are in 1 mole. It's at 6.02 times 10 to the 23rd. So if we have 0.5 moles, that means we have half of 1 mole. What should be our answer in terms of how many atoms are in half a mole? I hope you guessed it. It should be half of 6.02 times 10 to the 23rd, which in this case is going to lead us to answer C. Now, if you don't believe me, of course you can always pull out your calculator and do the nice calculation, 6.02 times 10 to the 23rd times 0.5. That makes things a lot easier for us. Now, if we need to go the opposite way, and we asking for the number of moles in 1.8 times 10 to the 23rd sulfur atoms, now in this case, instead of like we did before where we multiplied, this time we're actually going to divide, but we're still going to use the same number. Now, this is where that table still comes in handy. So I'm just going to go ahead and make my table, and I apologize for how bad it looks. But let's see. If I have 1.8 times 10 to the 24th sulfur atoms, if I have atoms here, that means to get rid of it, just like we did before, atoms has to go to the bottom. So I'm going to have 6.02 times 10 to the 23rd, sorry, atoms, and 1 mole. Now, that means I'm just going to be dividing these 2 values. Once I've done that, I'll actually come out with my value. Now, There's one of these answers we look at and we should be able to discredit easily. And that's going to be 1.1 times 10 to the 48th. That one is wrong. Horribly, horribly wrong. Never choose that one. But let's take a look at what we have here. If I punch it into my calculator, 1.8 times 10 to the 24th, I'm going to divide that value by 6.02 times 10 to the 23rd. I come out with 2.99, which is approximately, if you guessed it, 3 moles. This will be our actual final answer. Remember, not this. And we know it's not 1 mole because 1 mole would be 6.02 times 10 to the 23rd. So we have our final answer. Now, we're going to walk through a little bit more of this in terms of practice problems that you can use in class as well as out to be prepared for your tests. Now, taking a moment to look back at what we just covered. Where do you find yourself on this scale? Are you at a level 3? Can you explain why we actually have the mole? Or how, and also how to convert between moles and representative particles? Can you at least explain what the mole is and sort of give an idea of why we use it? And third, if you're at 1, I still have no idea what the mole is. Now, some of you may be hotshots and actually be able to take it a little bit further. If that's the case, see me. We're going to see what we can do to challenge you and to see how you can use this information even outside of this class. Well, that's all for now. I will talk to you in class and have a great evening.